Today we're going to talk about thermochemistry, chapter 6 in your textbook. And my guess is we'll probably have to split it somewhere in the middle. Oh, yeah, split it somewhere in the middle, finish on Tuesday. So, what is thermochemistry? We've had a snoop full of chemistry so far this semester. Just add some thermo to it, which is heat. All right. I can remember in grade school having this definition given to me. Energy is the capacity to do work, but it's also capacity to produce heat. Okay, got brandy. So that's about as broad a definition as you can make. What is energy? And then we have another law that describes what you can do with energy. You can't create it, you can't destroy it, you can only transform it. You can change it from one form into another. That's the law of conservation of energy. Another way to put that is in terms of the first law of thermodynamics. And we'll pick this up again later. I just thought I'd throw it in here so you could be thinking about it. First law of thermodynamics says that all the energy of in the universe, that's everything we've got now. We're not going to get any more. We're not going to get any less. So any changes that occur in the universe equals zero. Energy. The energy for the universe does not change. And that is the whole universe. It's everything we know and see. Most, in fact, I can't think of a single exception to this rule. Chemical and physical processes require transfer of energy of some kind. Sometimes you can detect it. Sometimes it's difficult to detect. But how do we detect a transfer of energy? Well, we need some sort of, we have to know what form it's taking when it moves. Right? When we talk about thermochemistry, of course, we mean heat. And that means you have to measure a temperature change. But other forms of energy can be transferred. Light, that's how we receive all the information we know about most of the universe. It's from light, and that is a form of energy. Only when we've ventured out into the close neighborhood with our robotic craft and, well, actually, a while back. Otherwise, the information we get, actually, we sent some probes to comets, a couple of comets, and brought some samples back. But most of the information we get is through energy. So I digress again. Energy can be divided into two forms. One is potential, the other is kinetic. Potential energy can take many forms as well. One of the most easily understood is positional potential energy. That is, when I get lifted from here to, say, if I go to Greenbrier campus, I teach on the 4th floor. So by the time I get to the 4th floor, I've added to my potential energy due to my position above the ground. And you can add potential energy on any heavenly body. You just need to be in a gravitational field. And if you put energy into that in the right direction, you can store that potential energy in an object above the surface. And then how do you get it back? Well, if it's being held up there by some force, you just remove the force and it'll spontaneously drop to the surface. And you get all that energy back as kinetic energy, energy of motion. So I could to go to the Greenbrier campus and jump out the fourth floor window and get all that energy back. And it'd be great until I hit the ground, and then I have to give it up again in the form of broken bones and smashed head and heat. But potential energy can take that form due to your position. Or more importantly for us, we can store potential energy in chemical bonds. That's where they reside for our purposes. So when we manufacture nitroglycerin, we put nitric acid, a little bit of sulfuric acid to help the reaction, and some glycerol. And it forms this layer, liquid layer on top, and that's your nitroglycerin. And you want to be very careful because there's energy stored in those bonds. And it's very unstable. Just sneeze real hard and it'll blow up in your face. But the energy nonetheless is in those bonds. Other forms of potential energy can take the form of electrostatic energy. If we try to remember, negative charges and positive charges attract. So if you get them close enough and then you restrain them, then that restraint is storing energy. Or if you try to push two positive charges together, you can get them so close and they start pushing against you. Well, if you lock them in that position, then they've got stored energy. If you release it, then they'll fly apart. Same thing with magnets. You put two north poles together and you can feel the push. Okay, those are examples of compositional potential energy. Kinetic energy is really easy to understand. It's just, if a mass is moving, it's got kinetic energy. Doesn't matter how big it is or how small it is. It can be the size of an atom, or it can be the size of a planet. It still has kinetic energy if it's moving. And that covers the whole universe. There's nothing that I know of in the universe that's not moving. So what do we say if it's not moving at all? It just completely stopped. Absolute zero. Okay, and you can calculate its kinetic energy in terms of this equation. Okay. All you need to know is the mass and the velocity of the particle or the thing, and you can calculate. Now, in the SI system, we have units of measure that are fundamental. Right? Mass is the kilogram. Okay. What's velocity? It's a derived unit, actually. Meters per second. So meters per second for velocity, but we got to square it. Right? So the unit of kinetic energy is kilogram meters squared per second squared. But we don't want to run around saying that all day long when we're talking about energy. So we created a new unit, and that's equal to a joule. Okay. You'll see that one a lot before we're done. The joule. Okay. This ball A has potential energy due to its position. And this B has less potential energy due to its position beneath A. Currently, A is being held in position. We don't know what's holding it there. It doesn't really matter. But if the force that's holding it there is removed, then it will spontaneously drop in that gravitational field and strike B. Okay. Now, if you know anything about collisions, there are two types of collision. There's a perfectly elastic collision, which means that the kinetic energy, the total kinetic energy before the collision, right before the collision, is equal to the kinetic energy right after the collision. That's elastic collision. Then there are inelastic collisions, and there are various gradations of inelastic collisions. And some of that kinetic energy is lost in the process. That makes it inelastic. So in this case, we would expect for an elastic collision, if A dropped to where B is and transferred all of its energy to B, then you would expect B to rise to the same height as A, right? Because we're conserving energy. That first law. But what actually happens? Well, B only makes it up to the first ledge. So where did that extra energy go? We can't create it. We can't destroy it. So we got to account for it. Where did it go? Turned into heat. Friction. Robbed us of some of that energy. Okay. Now, when we start talking about heat and temperature, they're closely related, but they're not the same. So let's look at the differences between heat and temperature. Heat versus temperature. Okay. Temperature is an intensive property. That is, if you are measuring the temperature of an object that has equilibrated, then all the temperature that you measure anywhere in that object will be the same. So it doesn't matter how much of the stuff you have. The temperature is the same, which makes it an intensive property. Whereas heat is an extensive property. I like to call it a capacity factor. It's easy to wrap my head around that one. And the amount of heat that you're measuring does depend on how much of the substance there is. And that's one fundamental difference. The other is temperature is you're measuring the state of the object right now. And what you're actually measuring is the average kinetic energy. Average kinetic energy of all the molecules. That's what temperature is doing. It's measuring that value. It's not giving it to you in joules, but the temperature is related to the average kinetic energy of all the molecules. Whereas heat is not measured as a state, a present state. It's measured as a transfer of energy between two objects. So this is based upon the transfer. Now, where are they related? They're related because the only way we can measure this transfer of heat is with a change in temperature. So if one object is hotter than the other one, when you bring them together, then heat will be transferred from the hot object to the cold object. It's always spontaneously from high temperature to low temperature. Okay, so those are the fundamental differences between temperature and heat. I mean, they're first cousins, and they cooperate, but they're not the same. Okay, more definitions, of course. What would we mean by work? And now you have sort of a general idea of what work is. Something you do for somebody else you get paid for, right? Not in chemistry and physics. Work has a quantitative definition. When work has been done, a force has been applied through a distance. Okay? Force times distance equals work. So if I when I roll that thing down the hallway, I'm pushing on it. And I go a certain distance in here. I've done the work. Force times the distance. But if I stand here and push on this board mounted to the wall, I'm applying force, but it's not moving. Right? So I'm not doing any work. By the way, I'm expending energy to do that. Where's the energy going? It's all being converted into heat. It's virtually wasted. Okay? But no work has been done. But I still had to expend energy, and we have to account for the energy. So where did it go? Well, we turned it into heat. Okay. So hang on to that definition. We'll come back to it. Oh, by the way, work is in terms of energy units. So it's in joules. Okay. So what's force? Force is in a unit called newtons. And distance is our SI standard, meters. So 1 joule is a newton meter. So what's a newton? A newton is based upon Isaac Newton's second law of motion. Right? He says that force equals mass times acceleration. Right? So if you apply a given force to a mass, it will accelerate at a definite rate. So our mass is in terms of kilograms, right? And acceleration is in meters per second, right? Meters per second is velocity. Acceleration is the change in velocity. So it changes velocity every second. That means second has to be squared. So this value right here is the newton. Kilogram meter per second squared is a newton. So if you substitute this one in here, kilogram meters per second squared times meters, then you have the joule equal to kilogram meters second squared per second squared. Just like before. Okay. They're all interchangeable. If you know where they came from. Sometimes you only need newton meters as your equivalent. If you need to do a calculation where you have to cancel units. But sometimes you've got mass terms in there, and you've got velocity terms or acceleration terms. Sometimes you have to work it all the way back to here in order to do the calculation. Otherwise, you're stuck because you can't cancel newtons if there are no other newtons in the terms. But if there are kilograms and meters and seconds in there, then use those. And you're going to resolve the equation units. Right? Remember, when you do a mathematical operation on a measurement, you are doing math on the number and the units. Okay, so we need to also define the difference between a state function and a path function. It's really very simple in words to define it, but in application, it's a little more difficult to wrap your head around it. So let's start with the easy part. How do we define a state function? It's any property that does not depend on how it got there. It doesn't depend on its past conditions or its future conditions, just where is it right now? Ooh, that was snuck up on me. Okay, back to our topic. So it's called a state function because the only thing that matters is its present state. Where is it right now? A path function, on the other hand, is one that does depend on the route taken to get where it is. So when we talk about heat transfer, when heat is transferred from one object and then to another object, then to another object, it'll give you a different value than if you transfer the heat directly from this object to the last object. Heat is a path function. As an example, whereas energy, total energy, is a state function. We're just defining what is it right now. Okay, so those are the fundamental differences between those two, state and heat. Work is also a path function. If I, let's see. If I try to slide a box up an incline to get to a certain height, I have to apply force over a distance to get it there. Right? So we can quantify the amount of work that was done. Whereas if the box is sitting at the location, except it's not high enough, then deadlift it to that height. That's a different amount of work that was performed. And the probable difference between the two is that there was no friction lifting it, deadlifting it. Whereas when I'm pushing it, sliding it across the ground, I'm losing a lot of energy and it requires more force than you would expect to overcome friction. So the amount of work that was done those two different ways are different values. But what is its positional energy? Its potential energy due to position? It's the same. You went from this height to that height. So it changed its positional potential energy by the same amount. And it didn't matter how it got there. Okay, that's the difference between a state and a path function. As an example. Okay. So we're going to have to define some things in order to discuss heat transfers. Right? When you're going from one place to another, we need to correctly define what is the area, mass, volume, whatever, that we're interested in describing. Because when heat transfers, it has to cross some boundary. Sometimes it's a narrow physical boundary between two objects when they're touching. Sometimes it's a more ethereal boundary, like gases mixing. But we have to define what that is, and that's called our system. And this is probably one of the best definitions: is a system is anything required to solve a problem. Right? We define the system, and then everything else is surroundings. Okay, I've got a little animation coming up here. Here it is. So if we say whatever is in here is the system, then everything else is surroundings. Okay, even out to the edge of the universe, if you want to go that far. Although many times it's more useful to also restrict the surroundings. Say we've got, say, I'm the system, and only everything else in this room is the surroundings. And we just block it off, and nothing gets in, nothing gets out. No matter, no energy, nothing. So we have defined the surroundings as just what's in the room, and I'm the system. That's often more useful than just saying the surroundings of the universe. It's a little hard to quantify the universe when you're discussing system versus surroundings. Okay, so here we've limited our surroundings. And that gold boundary is impenetrable. Nothing gets in, nothing gets out. What happens in Vegas stays in Vegas. All right. Okay. So we can define a system in this situation, or in any situation actually. We can define it as one of three different types. If it's an open system, then matter and energy both can cross that boundary. And there are many biological systems that are just like that. Except that with biological systems, this transfer of energy and matter is controlled. Otherwise, the biological system wouldn't function. But it's still an open system by our definition. The other possibility is we don't let matter cross the boundary, only energy. We don't let matter go across that boundary. Okay? And then you'll never guess what the third one is. Neither one of them can cross. And that's called an isolated system. So when the system has a boundary around it through which matter or energy cannot pass, neither one of them, then we have an isolated system. And this is often very useful in what we're going to talk about later. We may not get to it today, called calorimetry. When we measure heat, changes in heat in a well-defined system in the laboratory, we do that inside an isolated system. And that way, anything that happens in here stays in there, and we know that with delta E being 0 for the universe, for an isolated system, changes in energy inside that system are also equal to 0. Okay. Let's see. Keep track of my time a little better than you. All right. Okay. So when we describe a chemical reaction, when bonds are broken and reformed during that reaction, if the energy of the products, let's do it this way. So we have reactants yield products. Okay. And this has a certain amount of energy, and this one has a certain amount of energy stored in its bonds. Okay. If the energy stored in these bonds is greater than the energy stored in those bonds, that means we had to put energy in to build up that energy content of those bonds, correct? So if we do it that way, then energy becomes a term on this side. We add that energy in here, and now it's stored in these bonds. That's an endothermic reaction. We put energy in, now it's stored over here. The other possibility is energy in these bonds is greater than it is in these. So where'd that energy go? It's still conservation of energy. We've got to account for it. So if this one has more energy than these products, then the energy becomes a product. And that's an exothermic reaction. And it can be quantified through various measurements, but most often through temperature change. Okay. So we're going to start slow, build up speed, and try to develop some intuition about endothermic versus exothermic. Freezing of water. The first thing you have to do when you talk about freezing of water is define your system. Otherwise, you can't solve the problem by its definition. The system is whatever you define that helps you solve the problem. So what's the system here? Well, it's the mass of water that's freezing. and energy moves into it or it moves out of it. We have to decide what happens. The surroundings is everything else. Suppose you put a tray in your freezer with an ice cube tray with water. Okay. So the water is going to do what? In order to freeze, when it becomes solid, what does it have to do? It has to give up energy. It loses energy in the process. So if the system is water, it starts off as a liquid, then in order to turn to a solid, we have to give up energy. So energy has to leave the system. That would be an exothermic process. Okay. Now, how about this one? We're going to make it a little more difficult, but not too difficult. In other words, we're actually going to define the system for these possibilities. So in this case, your hand gets cold when you touch ice. And we're saying your hand is the system. And the ice is your surroundings. So what happens? Which way does the heat flow? From your hand to the ice, right? So that's an exothermic process. Okay? Ice gets warmer when you touch it. So now the ice is the system and you touch it, heat transfers where? Into the system. It's an endothermic process. Water boils in a kettle. That water, we have to add heat to it, right? So heat's going into the water to make it boil. Endothermic. Water vapor condenses on a cold pipe. So the water vapor, the gaseous water, is our system. And in order to condense, it has to give up heat. It transfers heat from the system into the pipe. That's exothermic. How about ice cream melts? Okay, the ice cream is your system. It takes heat from the air on a summer day. And heat has to flow into it to make it melt. It's an endothermic process. Okay? Now, for this one, we have to define our terms. We have to define our own system. Try to be most efficient and the most physically accurate. Methane is burning in a Bunsen burner in a laboratory. What's the system? Think about the chemical reaction that's taking place. Right? Methane, which is that, plus you mix a little oxygen in with it, and you make carbon dioxide and water. Okay? So let's see, let me balance these things. 2. There we go. So the system is the mixture of gases that we set on fire. And then the Bunsen burner itself, and maybe a student that's foolish enough to put their hand close to it. They're imitating Gordon Liddy. Remember G. Gordon Liddy in history? He was one of Richard Nixon, President Richard Nixon's lieutenants. He had a reputation for having a stone will. He would flick a lighter and hold his hand over it. He could smell the flesh burning and just hold it there. Okay. So if you're foolish enough to get close enough to that burner, then you become part of the surroundings. So what's happening? Well, during that reaction, heat is evolved, correct? Heat is being given off. Also light. And that transfer goes from the system to the surroundings. It's an exothermic process. How about water drops sitting on your skin? What's the system? I would focus on the water drops, wouldn't you? Sitting on your skin after swimming starts to evaporate. So if we do that, then the water drops are absorbing heat from your hand. That's an endothermic process. So it's all in terms of what you define the system to be. If you define the system to be your hand, then that would be defining an exothermic process, because heat is being released from your hand to make the water evaporate. Right? So either way, it's valid. You just have to define your terms. Some are easier than others. Let me put it that way. Hydrogen gas and oxygen gas react violently to form water. That is an understatement. There's your reaction. Right? At those temperatures, everything's gas. So we've got, let's see, 2 of these and 2 of those. Okay, when that happens, by the way, you ever seen the videos of the Challenger disaster? The space shuttle Challenger was, during the launch, just blew up. The rocket was on a cold January day, and the O-rings that were holding the solid rocket boosters together got too brittle. So gas blew past them and ignited. And it just blew that flame out against the big tank in the middle of that orange tank. An orange tank is filled with liquid hydrogen and liquid oxygen. Once they mixed and ignited, the whole thing just went kablooey. So lots of energy is released during this reaction. So if we say during this reaction, first of all, what type of reaction is it? It's exothermic, right? It gives off energy. So if we look at it that way, where's the energy term here? It's a product, right? Energy is a product. Now, when you look at it that way, it's easier to answer this question. Which is lower in energy, a mixture of hydrogen and oxygen or the water? Well, if energy is conserved, there's a certain amount of energy over here. There's a certain amount of energy over here. Only here, the energy is a separate term. So the total here has to be the total there. And if we're only focusing on this one, the amount of energy in water has to be less than the total of these two. See what I mean? It's all a balancing act. So water has the lower amount of energy stored in its bonds than either of these two. Okay. So we'll go back to thermodynamics for just a minute. Thermodynamics is simply the study of the energy and the conversions that it undergoes. It was they would say in my grandparents' day, all the rage in the beginning of the 19th century, the Industrial Revolution. Heat engines were being investigated, right? The first one was a really clunky thing that was used to pump water out of mines in England. It was a steam engine. They were capturing the energy that was contained in wood and then coal to drive this engine. And they wanted to know how to make it more efficient. So they needed to know, where is this energy coming from and where is it going? And how can we extract more of that energy and make mechanical energy out of it so that we can run our pumps more efficiently? So thermodynamics developed around in that environment where they were studying heat engines. So it's no mystery that the movement of heat spawned thermodynamics. But there are some laws that go along with it, as there 1, 2, and 3. And actually, they said they got to the third law of thermodynamics and said, oh, wait a minute, we forgot one. But they'd already got a number 1, so they went back and said a 0th law of thermodynamics. I think it's kind of funny. Anyway, the one we've already looked at, the law of conservation of energy, is actually the first law of thermodynamics. And it simply says that the total amount of energy in the universe is constant. There is no change in energy for the universe. But within a system, a defined system, you can get changes in energy, right? Because it's just a pocket of the universe. It's not the whole universe. So you can get energy changes within a system if you allow energy to cross that boundary between the system and the surroundings. Okay, and the definition of that change allows for either changes in heat or changes in work. Those are the only two ways that you can change this value for a system. And this is known as internal energy. The internal energy of the system is a sum of all of its heat content plus all the work that goes into changing it. Okay? And we use this little Q. That is equal to heat. And W we've already defined before. That's work. And how do we measure this transfer of heat? Change in temperature, among other things, other factors that are brought in, primarily temperature transfer or change in temperature. Work is a little more difficult to grasp. So in order to make it more manageable, we define work in terms of a change in gas. In other words, a change in volume, a change in pressure, whatever the case may be. And we work that into this definition. No pun intended. Although I'll have to remember that one. That was good. Okay. This internal energy, when we measure it, it has a number, right? And I would argue it also has a unit of measure. But since we usually talk of energy in terms of joules, then it's automatic. If you have the number and you're saying internal energy, you mean joules. But to be sure, there are other units of measure that have been used over the years. In fact, when I first started in the sciences, we didn't measure things in joules. We measured them in calories. Calories is easy to wrap your brain around, but it's more difficult to convert calories to other units of measure in the SI system. So they came up with a joule instead. But they are interchangeable, right? Nature just does what it does, and we define our measurements to keep up with it. Then you have a sign. So we need a sign convention. And that sign indicates what direction energy is flowing relative to the system. It's always based upon the perspective of the system. So if I'm the system, is heat coming in or is heat going out? Or work, is work being done on me or am I doing work on my surroundings? Okay. That's your sign convention. So if you have a system here, and these are all surroundings, if the system is losing heat to the surroundings, go in that direction, then relative to the system, it's losing. So the heat term is negative. Okay. If, on the other hand, heat's flowing into the system, then Q would be positive. Okay, it's all relative to the system. The other one, work, is a little more difficult to wrap your brain around, but if the system is doing work on its surroundings, and I'll show you how that happens in a minute. If it's doing work on its surroundings, the same sign convention is negative. But if the surroundings are doing work on the system, then it's a positive sign on that value. Okay? That's our sign convention relative to the system. And this just says what I said with a pretty picture. It's always the system's point of view. Okay. Let's see where we are. Okay. Well, that tells you some of the same stuff I already told you to do with that one. I think the next one is our video. Yep. You ever seen Professor Dave before? No. Here's your opportunity.
Hey guys, it's Professor Dave. Let's talk about thermochemistry.
He knows a lot about the science stuff. Professor Dave explains.
Thermochemistry is the branch of thermodynamics that deals with the heat absorbed or produced by a chemical reaction. A reaction can either be exothermic, one that releases energy, or endothermic, one that absorbs energy. This change in energy is represented by delta H, or the change in enthalpy for the reaction. For our purposes, we can think of the change in enthalpy as being the change in energy for the reaction, or the energy stored in all the bonds of the products minus the energy stored in all the bonds of the reactants. If there is more energy in the products, delta H will be positive, meaning the additional energy had to be provided, making it an endothermic reaction. If there is less energy in the products, then that additional energy was released, making it an exothermic reaction. Energy, which is the capacity to do work, can have many forms, like mechanical, electrical, chemical, heat, and so forth. And besides quantum mechanical exceptions, energy is conserved. That means it can change forms, like heat energy that evolves when the chemical energy in a broken bond is released. But it won't be created or destroyed. Heat, represented by the letter Q, is a trickier thing to define, but a good way to put it is that heat is the energy that flows between a system and its surroundings due to a difference in temperature. Heat will always flow spontaneously from an area of high temperature to an area of low temperature. For a system, Q will be positive if heat is being absorbed by the system, and it will be negative if heat is being released by the system. When temperature and pressure are constant, Q equals delta H, the change in enthalpy. When we discuss thermochemistry, we will discuss energies in terms of joules or kilojoules. Another common unit used by chemists is the calorie, which is equal to 4.184 joules. 1 calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. This is not to be confused with the food calorie, which is calorie with a capital C. This is actually equal to a kilocalorie, or 1,000 calories, also abbreviated as kcal. A thermochemical equation reports the change in enthalpy for a given reaction in stoichiometric terms. Here, the delta H listed is specific to the molar quantities given by the balanced equation. So if the number of moles of each substance as given were to react, the change in enthalpy would be as listed. To find the enthalpy change for a specific amount of material, just do some stoichiometry. If twice as many moles of material as are listed were to react, then the enthalpy change would also be twice as much as listed. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, professordaveexplains@gmail.com.
Okay. So he introduced some ideas and some terms here that we haven't talked about yet. The difference between heat and enthalpy. And we're going to get to that here pretty quick. And in that discussion, we'll also define when is heat actually equal to enthalpy. And just for your intellectual pleasure, remember this is a path term or path function, Q. This is a state function. So under certain conditions, they're equal in value. We have to define what that is, though. Most chemical reactions, in fact, all chemical reactions, when you look them up in reference manuals for the heat that is either produced or absorbed by that particular reaction, will be stated in terms of enthalpy. You'll never see Q. It's always delta H. Okay, so now we have an idea of heat transfer, but we need to get a handle on work on the system versus work by the system on its surroundings. And in this scenario, we have a gas that we allow to go from this state to this state. So it's going to expand from this position to this position. It will increase in volume. It'll have a delta V, a change in volume. And when it does that, we have fixed the pressure as constant. Right? The pressure is the same all the way through this process. The only thing that's changed is the height and consequently the volume. Okay, remember our definition. Work equals force times distance. So we need to find an expression for force out of this scenario. And then the distance, of course, is going to be that change in height. That will be our D term. Okay, so here we have our work equals force times distance. And we have pressure also by definition is equal to force per unit area. Right, here it is. Pressure is equal to force per unit area. And if we solve for force, then F equals P times A. And we can plug that expression right in here for that F. So P times A times D is work. Now what about D? Well, we're actually changing volume. So a change in volume, in this case, is a change in distance, that height, times the area. The area is not changing in this cylinder. It's just moving a distance. So now we have the change in volume is the height or the distance it moved times the area. And if we solve for D, then we get change in volume divided by A. We plug that in here. Now let's see what it looks like. Okay, we have pressure times area over here, and then we have delta V divided by area. So the areas cancel. The area term is gone. And all you're left with is P times delta V. So work, in this case, is a constant pressure and a change in volume. Now, which way is the work going? The system is expanding against constant pressure from the surroundings. So it's doing work on the surroundings. An expanding gas, let's just say it that way. An expanding gas always does work on its surroundings. A contracting gas, if it's under force from the outside, is always work being done on the gas or on the system. There's just one problem. Notice that when we calculate W, what's the term here? Pressure is a positive value, right? So that's positive. How about a change in volume? Remember, delta anything is always final minus initial. So this one would be the final volume minus the initial volume. So what's the sign? Which one's bigger? The final volume is bigger than the initial volume. So this one is also positive. So we got work is a positive value. But what do we say about everything is reference to the system? If the system's doing work on its surroundings, it has to be a negative value. So we have to fudge. We have to add a correction. So in terms of our system, W is equal to negative P delta V. That's our definition of work for a gas. Negative P delta V. Now, to be sure, in this scenario, we held pressure constant, but it doesn't have to be, right? This would also work for equals negative delta P times V. Let the pressure change too. Okay, it'd still be a measure of work. But you still need that negative sign to make the conventions fit. Right? Otherwise, the calculations will come out right. So what are the units of measure here? Well, one unit of measure is liter for volume, and that's SI system. And pressure is atmospheres. The atmospheres is not the SI unit, right? What's the SI unit for pressure? Remember? The Pascal. So SI units would be the Pascal meters. But more often than not, we measure pressure in terms of atmospheres anyway. So we're going to stick with that for now. So 1 liter atmosphere, if we want to convert this to a measurement that is useful in other calculations, we need joules. So once we calculate liter atmosphere's value here, we need to use this equivalence to convert to joules, right? And whenever you have equivalence, same rule as from the first day we started this class, whenever you have an equivalence, you have a conversion factor. Right? Okay. That value is in useful information. So you don't have to memorize it. Unless you want to. Or if you use it enough, you'll just remember it. Okay. Got a few more minutes. Oops, gave away the answer. So if we have, let's compare these two gases. They're both expanding. Right? So they're doing work on their surroundings. It should be a negative value. So how much work is being done for A? For A, work would be negative pressure, 2 atmospheres, times a change in volume. So what's the final volume? 4 liters. So it's 4 minus 1 liters. So that'd be 2 times 3, correct? Would be negative 6 liter atmospheres. That's for the first one. How about for the second one? Now let's say you've got a negative, and then pressure is 3 atmospheres. And what's the final volume? 3 liters. Initial volume is 1. So the difference is 2. So 2 times 3 is 6. Lo and behold, same amount of work has been performed by the system on its surroundings. Okay. This is going to crap out on me. All right, they both perform the same amount of work, apparently different conditions, but you still get the same amount of work out of it. Now, for this problem, we're looking at change in internal energy, delta E. So delta E is what? Delta E is equal to Q plus W. Do this down here. Okay, for the first scenario, we have an endothermic process that performs work on the surroundings. So an endothermic process means positive heat, correct? So for the first one, we have positive heat, and the system performs work on its surroundings means negative work. Okay? So in that case, if the absolute value of work is greater than heat, in other words, if the scalar quantity, if the values are bigger without the sign, if work is greater than heat, then delta E is negative. But if work is less than heat, then the value is positive. For delta E, internal energy change is positive. The converse of that is work is done on the gas and the process is exothermic. So exothermic means negative here and positive here. So you have just the opposite situation. If this term is bigger than that term, then E is positive, and if this one's bigger than that one, E is negative. Okay. Let's see, got a couple more minutes left. See if I can find a convenient place to stop. I was hoping we could get to a discussion of calorimetry, but maybe we'll do that. We'll do that right before the lab. Let's see if there's anything else in here. Yeah. While it's fresh on your mind, let me get through the next 2 or 3 slides and define when Q and delta H are equal and why they're equal. Okay. These are different values. One is a state function, one is a path function. So it does matter how you get where you're going because it represents a transfer of energy. Delta H is more a potential. So we can transfer energy into a system through heat, or we can transfer it through work, or it can come out either way. But those are the only 2 ways to change the internal energy of the system, with Q or W. And just to reiterate, change in internal energy is Q plus W. Right. Enthalpy, on the other hand, is best to think of that as a potential. In other words, the chemical reaction has the potential to produce this heat. It has the potential, with this value assigned to it, to generate a certain amount of heat, Q. Or to do work, actually. So it can produce heat and do work, which changes the internal energy of the system. Okay, so H, delta H, and delta E are both state functions. Now, the reason we're making such a big point of this is when you start to work with chemical equations and try to make sense of them in terms of you have a new equation and you want to know something about it, but you don't want to have to do the reaction. You don't have to measure heat transfer, temperature changes, whatever the case may be, changes in internal energy. The fact that these are state functions means that you can use information from other reactions to inform the Darling reaction that you're investigating. And that's just a lead-in to Hess's law, which we'll probably get to next week. Okay, so you'll just have to just take this one at face value, because it would require an extensive discussion of thermodynamics to explain what it is. And that's outside the scope of this chapter. We'll get some more thermodynamics later when we talk about entropy. But for now, just take this definition for what it is. A change in enthalpy is equal to the change in internal energy plus any changes in pressure times volume. And here you have this term, change in P times V. Like I said before, pressure and volume could change at the same time, right? So we know that delta E is Q plus W. So if we substitute delta E in here for Q plus W, then we have delta H equals Q plus W plus delta PV. But if we let the process occur at constant pressure, then we can pull that pressure term out. It's not changing anymore. But it's the same product, same mathematical product. So we pull that P out and just let the volume change. And when we do that, we find that work is equal to minus P delta V, right? We just defined that one, just proved that one. So if we substitute this one in for work here, and then we have this term left over, as long as the pressure is constant, and it's the same pressure for both of these terms, then this term cancels that term. And now you're left with delta H equals Q, but only at constant pressure. So if the pressure on your system is constant, then you can measure the heat transfer that takes place and equate that to enthalpy. If you don't do that, then they're not equal. Okay. Let's see. My past time already. Is it 40 or 50? 45. I've got 3 minutes. Let's say you're studying a process that takes a system from this pressure, volume, and temperature to this pressure, volume, and temperature. Okay? There are a whole number of different pathways that you can take to get there, right? You can change this pressure along the way and then maybe halfway through it, let the volume change. And you could start at a high temperature and then go to a low temperature, or you could flip it, go the other way, right? Allow all of these three to change. And we know how they're related from our gas laws. But there are many different paths that you can take to get from one state to the next. And along this pathway, Q and W both will differ. However, no matter what path you take, delta H is going to be constant. It's going to be the same, no matter what path you take. All those transformations, you'll end up at the same place, delta H. Delta H is a state function. So what are the state functions we've seen so far? Delta E, delta H, I think. These are states. And paths, we've seen Q and W. Path functions. So the nice thing about that is, if we know the enthalpy for the products and we subtract the enthalpy for the reactants, we can determine the enthalpy for reaction itself. And if you can do that, of course, recognizing that P1 has to equal P2 in order for this value to equal Q. If you don't care whether they're equal, then you can just go on your merry way and just say, all right, this is the enthalpy potential for reactants, this is for products, subtract the two, and you get the delta H for the overall reaction. Okay. So I'll make one final statement and then we'll break for the weekend. When Professor Dave showed you that reaction, whatever his reaction was, and a delta H assigned to that reaction, it's in terms of the whole reaction. This is how much heat you will get from that reaction. That's the enthalpy change for this reaction. Now, if you need to interpret that value in terms of propane, then it's this much per 1 mole of propane. But if you need to interpret it in terms of carbon dioxide, then it's this much heat per 3 moles of carbon dioxide. It's per, and I've seen some textbooks say per mole of reaction. And maybe that helps you understand it, but I think it's ludicrous because a mole just doesn't speak to reaction. It's in terms of individuals. But this value is for the whole reaction, and you can interpret it depending on what you need, either in terms of oxygen, carbon dioxide, water, or propane. Okay? And that means if you're going to change this in any way, say if you need twice that much for a reaction, multiply 2 times everything in that reaction, then you'll double this one also. Or if you need the reaction in reverse, if you flip it, then the sign changes. Okay? So we'll pick it up here next Tuesday. Just make myself a note.